Hello, in this video I'm going to say something about the Higgs boson, which is going to be no easy task because this is touching on some very complicated areas of physics. But the Higgs boson is also very well known now. It's sort of in the popular culture and such like since it was discovered back in 2012, and there was a big hoo-ha about it all over the media. So it's well worth knowing something about it and at least knowing what's important about it, even if we can't get into the details because it's just that bit too complicated at the moment. So let's take a step back to what we know so far. We've discussed the standard model of particle physics, which is our framework for describing fundamental particles and how they interact with each other. And there's a couple of features of the standard model which are particularly important when it comes to telling the story of the Higgs boson, and that is symmetry and something known as gauge invariance. So we've come across the word gauge previously because when we were laying out the fundamental particles in the standard model, we listed a whole load of things called gauge bosons. And if you remember, these are the force carriers in inverted commas. So for each one of the fundamental interactions, there is one or more gauge bosons, which is an exchange particle. So if you've got two particles engaging in the electromagnetic interaction, they exchange the gauge boson associated with the electromagnetic interaction, which in this case is the photon. Now, at the macroscopic level, when you aggregate all that up, it gives rise to a force, as we've described in classical physics. But we've got these interactions, this exchange of particles going on at the quantum level in particle physics. So we've come across the word gauge there, but as to what gauge actually means and why these things are called gauge bosons is very, very complicated. But we can, at a simple level, think of gauge as being some kind of measurement. So when we're describing all of the interactions and behavior that's in the standard model using quantum mechanics, and all of the, it's broken down into various different theories, we have all of these fields. So each interaction has got a field which permeates space. We can't directly get at that field. We can't go out and say, okay, let's go and observe the electromagnetic field directly. We can observe the effects of the field. We can observe what the field gives rise to. So we might make some observation of some kind of thing here, some kind of measurement. So this is getting to this measurement idea associated with gauge. So we've observed something. The thing is, in the underlying field, you've got lots of different configurations which can give rise to the same observed phenomenon. So we've got lots of potential options here of what's going on. Now, these different configurations in the underlying field are all related by various symmetries. And this is one of the powerful ways of describing what's going on inside the standard model. The way it's describing things is looking at these symmetries. And it's also saying this gauging invariance is saying, well, this bit hasn't changed. Our measurement isn't really changing around much. But we've got something which is changing underlying it all, built on these symmetries. So you've got something that hasn't changed, this invariance, and that is based on these symmetries underlying it all. So this combination of things, these two things, the symmetry and the gauge invariance, was very, very successful in the early days of particle physics and quantum mechanics in predicting a lot of stuff. And it was very good with the electromagnetic and the strong interactions. But there came a problem with the weak interaction in the 1960s. That the predictions made by this symmetry and the gauge invariance, the predictions were saying that the W and Z bosons, which are the bosons associated with the weak interaction, that they would have zero mass. Yet observations were saying the opposite. So that was the prediction of well, it hadn't become the standard model yet, but it was the prediction of the theories of the time that they would have zero mass. So what was going to be done about this? There needed to be a new theory, essentially. Something had to be added in to everything that was known or changed in order to explain the observed mass of the W and Z bosons. So a whole load of scientists were working on this. There was the suggestion that this symmetry would sometimes break down, and that would allow for different processes to take place and for mass to be placed on these W and Z bosons. So lots of people were investigating this, most notably Peter Higgs. It's all named after him. So in order for this to happen, we needed a new field, a new boson, and a new interaction. And all of these are named after Higgs. You've got the Higgs field, the Higgs boson, and the Higgs mechanism. So all of these were put together. They were incorporated with all the other theories that were going on. And in the 1970s, that's when we got the Standard Model. So this was built into the Standard Model from the start. That, well, if all of this happens, then it explains our observations. The trouble is, Higgs bosons are extremely difficult to find. They're very hard to detect. They're very unstable. So it's taken a while to get the experimental equipment, i.e. CERN, the particle accelerator and collider in France, Switzerland way. So once that was built, it gave the capability to try and detect these Higgs bosons, because you can't just go and observe the field for the same reason as we were saying back here. You can't just observe these fields, you observe the effects. Anyway, in 2012, long story short, they put together the experiment, they got the data, and lo and behold, they managed to get evidence that they detected the Higgs boson. So big tick in the box for the Standard Model of particle physics, that this that's been built into it for 40 years has now been validated to some extent. So that then means we can start making more predictions about the Higgs field and the Higgs mechanism and how all of that behaves. So that's one important thing about this Higgs boson, that it has validated to some extent the Standard Model. I mean, the Standard Model has still got other problems, but that was the big one that really needed to be addressed. The other thing, which is what gets picked up a lot in the news at the time as to why it was so important, is they go on about, oh yeah, the Higgs boson and the Higgs mechanism, it gives mass to particles. Yes and no on that one. So quarks and charged leptons, so electrons, positrons, things like that, and of course the W and Z bosons. Now, yes, the Higgs mechanism does give mass to those particles, but it's very easy, particularly for the layman, to be confused by what that actually means. Because when they're saying, oh yeah, it gives mass to particles, you say, okay, well, all of the mass that we observe in the universe is a result of the Higgs mechanism. Well, no, it isn't. Not true. First of all, not all particles get their mass from the Higgs mechanism. Okay, these are the important ones to a large extent, the quarks and charged leptons. But recall from what we were saying in the previous videos that around 99% of the mass of baryons, so baryons as being hadrons with 3 quarks, so stuff that's made of quarks, it's got 3 quarks. So this is the stuff that we're made of. Protons and neutrons are baryons. 99% of the mass of these baryons is coming from the binding energy inside the nucleus. This is the gluons as described by quantum chromodynamics. This is the strong nuclear force. This is the energy binding all of these quarks together in the nucleus of an atom. 99% of the mass is coming from the mass of that energy. So saying that the Higgs mechanism is giving mass to fundamental particles, well, yeah, okay, the mass of quarks and electrons and these W and Z bosons and various other things, that is coming from the Higgs mechanism, but it's not anywhere near the vast majority of mass that we encounter, because that is in that gluon binding energy. So you need to be careful about saying that the Higgs mechanism gives rise to mass. Yeah, it does, but don't leave out the vast majority, which is coming from other sources. So I think that's about all I've got to say about the Higgs boson, really. That gives this, very high level overview of what's going on, and maybe some of the pitfalls that you can fall into in misunderstanding why it's so important. But it is still epically important. I mean, this is one of the groundbreaking discoveries of the 21st century. Something that people had been after for a very long time in order to validate at least that part of the standard model. So hopefully that's helped a little bit in order to get a clearer understanding.